Welcome, everyone, to the Ontology Summit 2026. Today is the 1st of April, 2026, and we now begin the Foundations and Tools track of the summit. This track will examine the foundations of ontologies from a number of perspectives. We have a number of invited speakers. Today we have Evika Madali. Welcome. And in upcoming weeks, we will have Mark Musin, Nicola Guarino, and then on the 22nd, we'll have a synthesis. Today, I'm going to talk about foundations in general, with specific examples from mathematics, databases, and ontologies, of course. So, beginning with mathematics, it's not that well known, perhaps, that mathematics was pretty informal up until close to the end of the 19th century. It wasn't until Cantor came along that anyone thought of sets as being anything but some obvious thing. No one thought that one should check or think about sets as a theory. So Cantor was the first to do that, and very quickly he discovered that mathematics is inconsistent. This came as quite a shock to people, as you might imagine, and became very controversial, not only among mathematicians, but also among philosophers and even theologians. Catholic cardinals got into the fray, and even the Pope at the time. As a result of all this controversy, foundations in mathematics became a serious study for the first time. And after the controversy settled down a little bit and a resolution was agreed upon, set theory became the foundation of mathematics to this day. But it wasn't really enough, as you might imagine, and other foundation proposals emerged, particularly because some people felt that the set theory foundations were not enough, they didn't capture everything. So around the middle of the 20th century, category theory was developed. A category is a structure with objects and morphisms. In fact, you can just think of a category as being a very special kind of multigraph. But the key thing is that it abstracts common features of a wide variety of mathematical structures. And so it actually makes sense that it could be a foundation for mathematics. So category theory could provide interoperability among different fields within mathematics by having a common terminology. And you could then relate different parts of mathematics by means of functors, which relate one category to another one, preserving the structure. However, it was criticized as being a little too general, that you really couldn't say too much. It was derided at the time as abstract nonsense. However, over time, it did become accepted, and various specializations emerged that started to capture more of mathematics. One of these techniques that was used, and is quite common in category theory, is called internalization. This is a frequent theme. The idea is that you specify concepts within category theory in terms of objects and morphisms. It's related to the process of reification that is a frequent theme in computer science. Let me give you an example of this, the Cartesian product. So first, let's look at the kind of basic classical set theory idea, not the internal one. So The idea is that a Cartesian product is a set of ordered pairs. Sounds reasonable. But in the internal approach, you now treat a Cartesian product as an object defined by projection morphisms. So just to be brief, the external point of view defines this Cartesian product by looking at the internal structure, and the internal point of view defines a Cartesian product by considering its external relationships to other objects. So you got that? Now let's look at a topos. A topos is a category that internalizes a number of important set theoretic concepts. In fact, you could think of it as being an internalization of set theory. So it could then be another way of founding mathematics, but by means of internalization rather than this set theoretic external approach. So I'm going to describe the topos requirements by analogy with the relational algebra. As a result, we're now going to look at the foundations of databases. So although relational algebra is not actually a topos, the relational algebra is very well known and it's popular. And I guess most of you would certainly know what I'm talking about. So let's look at the relational algebra, the foundation of relational databases. So the key idea of relational algebra is that it has these three operations: project onto a subset of columns, join relations to form larger relations, and select the subset of a relation that satisfies a predicate. First, the relational projection operation. The first requirement for a category to be a topos is that there is a product object for every pair of objects. And as you can see, the product is internalized in a topos using an object and two projection morphisms. So the projection operation is one of the key requirements for a category to be a topos. It's also important within just set theory because the Cartesian product is so important in set theory. Next, let's consider the relational join operation. The simplest join is on two tables, each of which has a column with the same type. So I'll make a little diagram here that shows the join relation, the two projections to the tables that are being joined, and then some links to the common column type where we set those two columns to be equal. Well, the internalization in categories have the same notion, except that it's called a limit. So it has the same diagram that defines it, except that now these are all morphisms. So you have two morphisms from objects down to a common object. And this is generalized to many objects being joined together. The second requirement for topos is for any finite number of objects and morphisms, one can join them together. Rather, they can be limited together. The next operation is the relational selection operator. So far, a topos has project and limit, but it has no logic. This requires predicates. Well, predicates requires a notion of truth. Topos theory reifies truth with a truth value object, also called a subobject classifier. For the topos of sets, classical logic is true and false, Boolean. The topos of digraphs, directed graphs, I'm not going to cover that, but it's in the appendix in the slides. is non-classical. Its truth value object is not just true and false, it has other parts to it. The third topos requirement is that it must have a truth value object. And the relationship between a subobject and the truth value object is that the predicate, you have an object, you have a morphism, predicate morphism to the truth value object, and that defines via a limit actually the subobject of the object that satisfies the predicate. Is this helpful? Does it really tell us anything useful? Well, maybe it does. There are a number of advantages and disadvantages, though. One thing it does is to change some second order expressions into first order. That can be quite helpful for logical purposes. You reduce to first order logic. You can increase applicability. Reification is important in a number of areas in computer science that I, and I'm sure many of you, have contributed to. And one key thing is that it implements many forms of logic. So it's not just Boolean logic, classical logic, but others. Other disadvantages, it's conceptually more difficult, can be a steep learning curve to fully understand topos theory. And unfortunately, different toposes and reifications may not be interoperable with one another. So let's kind of summarize and compare foundations for mathematics and ontologies. Topos theory certainly has the potential to be a foundation for mathematics. It has the necessary ingredients. Well, I didn't tell you all of them. There is one more requirement, but it's in the appendix. And with that, you can pretty much do everything that you can do in set theory, but in a more general setting with multiple logics. Foundation ontology could also serve as the foundation for ontologies. So it looks pretty common there. Topos theory does require a bit of a learning curve, but then the same is true for foundation ontologies. However, there are many incompatible topos theories. The one I gave you is actually only one of them. And same appears to be true for ontologies. There are a number of foundation ontologies. Maybe they're compatible, maybe not. There's some disagreement about that. For the majority of mathematicians, that's not a problem. They don't really think too much about foundations. Although mathematicians are aware that they're using set theory, and I would say a fairly large number of them are familiar with category theory. Not so many with topos theory. For many ontologists, the lack of a foundations is not a problem also. But one interesting thing is that modern set theory and category theory are very deep and successful. They've opened up huge areas of study. And the question is that going to be true for ontologies? So that little blank space over here, hopefully will be filled in a bit during our track. And one more thing, this is the last slide that Ram presented at his talk, Ram Sriram. Hopefully now you can better understand this last column here after what I've told you about topos theory, category theory, and the foundations of mathematics. So with this,